Welcome to this AP Calculus lesson. In this presentation, we will go over fundamental theorem of calculus, average value of a function, mean value theorem for integrals. Down here at the bottom, we have two new topics, definite integral as a function, and the second fundamental theorem of calculus. So the top three should be review for us, and the bottom two are new topics. Fundamental theorem of calculus, if you recall from our notes, we said that if we take the antiderivative of the function little f of x on the interval ab, we would get the antiderivative, which is big F of x, and that's from ab still. One comment we made was we no longer need the plus c with definite integrals. So when we see bounds of integration, it means we have a definite integral and we don't need the plus c. So this is our antiderivative function. And now the fundamental theorem of calculus says plug in the top bound first. So we get big F of b, and we subtract, plug in the bottom bound, big F of a. Okay. Here are some examples we can work out together. First, we want to find the antiderivative function without the plus c. 1/3 x cubed minus 3x with our bounds of integration. Fix that 1/3. Good. And now we plug in the top bound. So I'm going to use brackets here. And this is just to say that we're doing f of b right now. So we have 1/3 2 cubed minus 3 times 2. This is our f of b. And now we want to subtract our f of a. So we have 1/3, 1 cubed minus 3 times 1. This is our f of a, using that fundamental theorem of calculus. Now we can simplify this expression. 2 cubed is 8, so we have 8/3 minus 6. That's still our f of b. And then 1 cubed is 1, so we have 1/3 minus 3. This is our f of a. And let's simplify this. We have 8/3 minus 6 minus 1/3. The double negative gives us a plus 3. 8/3 minus 1/3 is 7/3. Negative 6 and 3 is minus 3. But we want to express that 3 in terms of thirds, so let's replace that minus 3 with a minus 9/3. And now we can see that denominators match, and we have 7 minus 9 is negative 2 over 3. That is the answer to our definite integral. If we want, we can test this out in our calculator. So we hit math, 9. The bottom bound is 1. The top bound is 2. Our function is x squared minus 3. Our variable of integration is x. Hit enter. Negative 0.6 repeated. Math frac. Negative 2/3. That matches what we got in our work. I'm just going to clear some of this out so that we have room for our next example. So with this example, we need to first do a rewrite. We need to express the square root using exponents. So for example B, we're going to rewrite the integral from 1 to 4, 3 times x to the half power dx. And now we want the antiderivative of this function. That gives us 3 times x to the 3/2 power divided by 3/2 from 1 to 4. And anytime we divide by a fraction, it is the same as multiplying by the reciprocal. So it's 2/3 times 3 times x to the 3/2 power on the interval 1, 4. We see that the 3's are going to cancel, and we now have 2x to the 3/2 from 1 to 4. When we apply the fundamental theorem of calculus, it's 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. 3/2 exponent means the bottom is the root, so that means we're going to take the square root and then we're going to cube it. So the square root of 4 is 2. When you cube it, you get 8. So you have 2 times 8 minus 1 to any power is 1. That gives us 16 minus 2. We get 14 for our answer here. Again, if we'd like to check it in our calculator, Math 9, we're going from 1 to 4. The function is 3 times the square root of x, and the integration variable is x, and we get 14. Good. So I'm going to clear out this work again so we can do our last example here, example C. So the first thing we need to look at here is secant squared x. This is one of our memorized antiderivatives. So we say what function's derivative is secant squared. And you should say, well, the derivative of tangent x is secant squared x. So that means that the antiderivative of secant squared x should give us tangent x. So now that we have our antiderivative function and our bounds, we can apply the fundamental theorem. Tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1 minus tangent of 0 is 0. We get that this antiderivative, or this definite integral, is equal to 1. So those were just some review problems with our definite integrals. Next, we want to review the average value function. If f is integrable on a closed interval ab, then the average value of f on that interval is given by this formula, 1 over b minus a times the integral from a to b of f of x dx. If we were to examine a simple functions like x squared, where x is on the interval 1, 4, we can find the average value of f. Average is equal to 1 over, this is our a, this is our b, so 4 minus 1 times the integral from 1 to 4 x squared dx. So we've plugged everything into our formula. Now we can simplify this. The average is equal to 1 over 3. The antiderivative of x squared is 1/3 x cubed, and the bounds of integration from 1 to 4. I'm going to combine this constant. That gives us 1/9 x cubed, 1 to 4, which is 1/9 4 cubed minus 1/9 1 cubed. So 1/9 times 64, my marker, minus 1/9 times 1. If we factor out the 1/9, we get 64 minus 1, which is 1/9 times 63, which is 7. So the average value of x squared on the interval from x equals 1 to x equals 4 is 7. The mean value theorem for integrals states if f is continuous on the closed interval ab, and then there exists a number c in that interval ab such that the definite integral of f of x from a to b is equal to f of c times b minus a. Now, we can rearrange this formula. If I divide both sides by b minus a, we see that we get, let me change that to an arrow. We see that the left-hand side here becomes 1 over b minus a times the integral from a to b f of x dx equal to, and the only thing left on the right-hand side is f of c. And I do this because we can express this verbally. We can say that there exists a value c such that the function is equal to its average on the interval ab. There exists a value c such that f of x is equal to its average value on the interval AB. And this is true because it is a continuous function, so all of the intermediate values in between exist, and that means that there must be an x value that we're calling c, that if we plug into the function, it will be exactly equal to the function's average. So this example asks that we find the average value of the function f of x on the interval 1, 4, and then to solve for the c value predicted by the mean value theorem. So let's find the average value first. From our interval, a is equal to 1, b is equal to 4. So the average is 1 over 4 minus 1 times the definite integral from 1 to 4 of 3x squared minus 2x dx. The average value is 1/3. The antiderivative of this function is x cubed minus x squared. And the fundamental theorem of calculus tells us to plug in the top bound first. So we have 4 cubed minus 4 squared. Plug in the bottom bound, 1 cubed minus 1 squared. 1 raised to any power is 1, so this term is 0. Our average value is 1/3 times 64 minus 16. That gives us 1/3 of 48. Our average value is 16. I'm going to put that up here. Average equals 16. And I'm going to clear out our work so we can do the second part of this problem. And now we want to solve for that c value predicted by the mean value theorem. So to do that, we want to set the function f of x equal to its average value. And solve for x. So 3x squared minus 2x equals 16. This is a quadratic. We get 0 on one side. And now the first and last value multiplied gives us negative 48. We need two numbers whose product is negative 48, but whose sum is negative 2. So that's negative 8 and positive 6. We'll split up this middle term of negative 2x. So we have a 4-term expression. And the left two terms have a GCF of x. factor out dx, and we have 3x minus 8. The right two terms have a factor or a GCF of 2, factor out 2, and we have 3x minus 8. So this makes our one factor, x plus 2 times 3x minus 8 equal to 0. And if we set each factor equal to 0 and solve, we get x equals negative 2. And 3x minus 8 equal to 0 gives us x equal to, my marker, 8/3. We have to go back and look at our interval from 1 to 4, and we should see that x equals negative 2 is not in that interval. We discard it. This is our c value. It's possible to have one or more c values. In this case, we only have one. The other one we had to discard because it wasn't in the interval. So next, we want to use the definite integral to write a function. We're used to the definite integral having constants on the bounds, and now notice that we can have a variable on the bounds of integration, and this variable allows us to write a function. Notice that this is the capital F. It's the antiderivative as a function of the definite integral of little f with a variable in the bounds. So let's look at an example. So f of x is equal to, I'm missing my bounds here. Let's make this from 0 to x. So f of x is equal to the definite integral from 0 to x of t squared dt. And we see that the antiderivative here is 1/3 t cubed on the interval 0 to x. And now we plug in the top bound, 1/3 x cubed minus 1/3 0 cubed. We get that f of x is equal to 1/3 x cubed. So that's our function that we got using the definite integral and a variable on the bounds of integration. Now we're asked to evaluate f of 2, which is 1/3 times 2 cubed, so we get 8/3. And then we're asked to evaluate f of 3. 1/3, 3 cubed. I can cancel out a 3 with a 3, so it's 3 squared. So we get 9 for f of 3, and that's a capital F of 3. So this has its benefits. If we were looking at definite integrals from 0 to 2 and from 0 to 3, we'd be solving them twice. But instead, we solved it once as a function and just plugged in different bounds. And then we're able to plug in the different bounds of 2 and 3. Here's another example. In this example, we have a trig function. So again, f of x is a definite integral from 0 to x. And it doesn't have to be from 0. It could be any constant on the denominator, on the lower end of the bounds. So the antiderivative of cosine of t is sine of t. And our bounds of integration are 0 to x. So f of x is equal to sine of x minus sine of 0. F of x. Since sine of 0 is 0, f of x is equal to sine of x. And then we can evaluate this for all of these different values. We can say f of 0 is 0. We can say f of pi over 6 is 1/2. F of pi over 4 is root 2 over 2. F of pi over 3 gives us root 3 over 2. And f of pi over 2 is equal to 1. I'm just going to insert a new slide and say, what if we evaluate a function that is a definite integral that doesn't have 0 as the bottom bound? Change that. The variables have to be different. So now, if we were to find the function f of x, it's going to be the antiderivative, which is 1/4 t to the 4th from 1 to x. F of x is 1/4 x to the 4th minus 1/4 times 1 to the 4th. F of x is 1/4 x to the 4th minus 1/4. So you see that we could have a different lower bound than 0. It just adds a constant component to our function f of x. And now if we wanted to, we can evaluate at x equals 2. So f of 2 would equal 1/4 times 2 to the 4th minus 1/4. F of 2 is 2 to the 4th is 16 divided by 4 minus 1/4. We have 3 3/4, or we can say f of 2 is 15/4. So just to illustrate that the lower bound doesn't have to be 0, we can put a different constant there. Now here's another part where that definite integral as a function becomes helpful. We want to use the second fundamental theorem of calculus. The second fundamental theorem of calculus says that if we take the derivative of the integral with a variable bound, we can simply rewrite the function with a different variable. So just to illustrate this, d dx from 3 to x for t squared dt is equal to x squared. We just took this function and rewrote it in terms of x, because if you're going to integrate and then take the derivative, you're going to end up with the same function, just swapping out the variables is all you're doing. And that's what the second fundamental theorem of calculus is saying. Now, we can solve this the long way and see that we get the same answer. D dx from 3 to x of t squared dt. So with parentheses, you always work from the innermost set and work your way out. The antiderivative of t squared is going to be 1/3 t cubed. So we found the antiderivative. The bounds of integration are here. Now, the fundamental theorem of calculus tells us to plug in the top bound first. We have 1/3 x cubed minus 1/3 times 3 cubed. Now, if I take the derivative of 1/3 t cubed, that's 3 times 1/3, which cancel each other out. Subtract 1 from the exponent, we're left with x squared. And what is the derivative of a constant? Derivative of a constant is 0. So our answer is x squared. Notice that's what we got up here. Instead of doing all of this work, the second fundamental theorem of calculus says we have a shortcut. We can just swap out the variables and keep the function the same. So, solve with the second fundamental theorem of calculus. We're going to swap out the variables and keep the function the same. Cosine of x cubed. Now, the only thing that's different about this one is we don't have just an x up here, we have an x cubed. We replaced t with x cubed. Replaced t with x cubed. Well, if t is equal to x cubed, then what is dt? dt is the derivative of t. So what's the derivative of x cubed? 3x squared. That means that this dt should be replaced with 3x squared. And it's just customary to write the 3x squared in front of the trig function. So we just solved this using the second fundamental theorem of calculus, and this is the answer we got. We did a swap out of variables, but then we noticed that the swap out was not a simple x, it was something more complicated where the derivative was 3x squared. If t is equal to x, then the derivative is 1. And that's why we didn't have to do that in the past example. So if we go back to this example, if t is equal to x, dt is equal to 1, and 1 times x squared is x squared. We don't have to account for that 1. But here we see that dt was 3x squared. And we'll solve this one again the long way just to show that we get the same answer. So what's the antiderivative of cosine of t? So we say f of x is equal to, the antiderivative is sine of t from pi over 2 to x cubed. Now we plug in the top bound. F of x equals sine of x cubed minus, when I plug in pi over 2, sine of pi over 2 is 1. All we did so far is find the antiderivative. Remember, the fundamental theorem of calculus is talking about, let me go back. Fundamental theorem of calculus is talking about taking the derivative of the antiderivative. So we want to account for that. Derivative and antiderivative. So far, all we did was the antiderivative. That means that f prime of x is equal to the derivative of sine of x cubed minus 1. What's the derivative of sine? Derivative of sine is cosine of x cubed, but what rule do we need to use? Chain rule. We have an inside and an outside function. So what's the derivative of x cubed? 3x squared. What's the derivative of minus 1? 0. So we got 3x squared times cosine of x cubed without using the second fundamental theorem of calculus shortcut. Over here, we use the shortcut. Let's run through that shortcut one more time. A little bit of lag here. All right. We want to find the derivative of f of x equal to this antiderivative. So f prime of x is the derivative of this antiderivative. So we can just do a swap here. Cosine of x cubed. But now we said that we let t equal to x cubed. That means that dt is 3x squared. So f prime of x is 3x squared cos of x cubed. This is the shortcut by fundamental theorem of calculus part 2. This was working it out with the finding the antiderivative, plugging in the bounds of integration with fundamental theorem of calculus, then evaluating the derivative with chain rule, and we got the same answer both times. So watch the video, take notes, complete the practice problems, email me with questions. We can set up a meeting if you need to.